Hi AP Stats. Today we're going to take a look at lesson 9.3 day 1. Our targets today are we are going to perform a significance test about a population of a mean. And before we do that, we're going to have to state and check the random 10% and normal large sample conditions for performing a significance test about a population mean. And we're also going to have to calculate the standardized test statistic and p-value for a test about a population mean. So had we been in class, we would have done this exercise here. It says it's recommended that teenagers get 8 hours of sleep at night. Mrs. Cowles believes her AP Stat students are getting less than the recommended 8 hours of sleep per night. To test her belief, she took a random sample of 10 students in the class and recorded the number of hours of sleep for each. Do these data provide convincing evidence that the AP Stat students get less than 8 hours of sleep per night using a significance level of 0.05? So obviously we weren't in class, so I used another teacher's data, and here were 10 random students' hours of sleep, and I have them listed at the top. Now it says to calculate the sample mean and standard deviation. You can use your calculator and run the one variable statistics. The mean number of hours of sleep for the sample was 6.55. The standard deviation for the sample was 1.771. So state the appropriate hypotheses for a significance test. Be sure to define the parameter of interest. Well, a parameter of interest is the true mean hours of sleep for AP Stat students at Henry Ford II High School. So our null hypothesis is that the mean is going to be 8 hours. But the alternative hypothesis is we suspect that they actually get less than 8 hours of sleep. So what conditions must be met? Well, the random condition is met. Okay, so for the 10% condition is 10 times 10 less than the population of all AP Stat students at Ford. Well, 100 is not less than the population of AP Stat students at Ford. There are around 60 AP Stat students. So no, this condition did not check. Anytime a condition does not check, we have to proceed with caution. We're not going to stop the test, but we're going to proceed with caution. We're going to check our normal condition. Well, our sample is not greater than or equal to 30 because it's a mean. We use the central limit theorem to check it. So what we will do, since it's not a large enough sample, we can go ahead and we're going to give evidence that there's no strong skew or outliers. And you have to do some type of graph. I tend to do box and whisker plots because I can put it in my calculator and see very quickly if there is any strong skew or outliers. And you have to draw it on your paper. So we plot it, we see there's no strong skew or outliers, so therefore it is normal. So give the formulas for mean and standard deviation of the sampling distribution of the mean sample and calculate the values. Well, the mean of the sample is going to be equal to the true mean, which was 8 hours, okay, because that was the mean from our null hypothesis. We use the mean from the null hypothesis for that. When we do standard deviation, of the sample, we take the true standard deviation and divide by the sample size. Well, we don't know the true standard deviation, so we're going to use our standard deviation from our sample that we calculated, and divide by the square root of n. So we can see that this is the formula we're going to use, and this is also what we're going to use to calculate the mean. So our mean is 8 hours. Our standard deviation for the sample is approximately 0.056. Now, draw a picture and then calculate the test statistic. Remember, we're sampling we're using means, so we are not going to calculate a z-statistic. When we calculate a test statistic for the mean, we calculate the t. So just like before, our t is going to be our statistic minus our null value over our standard deviation. So go ahead and you're going to plug that in, and we get negative 2.589. Now we're going to go ahead and draw our curve. We know it's approximately normal. It's not a z-statistic, it's a t-statistic, so we call it t, but we're still going to have our mean of 0. Negative 2.589 is over here, and we're going to shade everything to the left because of our alternative hypothesis being less than that. Now when we do a t, the test statistic is a t, we have to calculate the degrees of freedom, or sample size minus 1, and you have to have that labeled when you draw your picture. So in this case, our degrees of freedom is 9. Since we are working with the means, the test statistic is a t-value. So we're going to use table B to find the p-value. So using table B, you're going to go to the row of your degrees of freedom, n minus 1. In this case, our degrees of freedom was 9. So we're going to go to row 9, and we're going to find the closest t-values and match the tail probability. The p-value will be a range between two numbers. So again, our t-value is negative 2.589. So I'm going to scroll over to our table. That would be in your AP formula sheet. And we find our degrees of freedom, and it was what? It was 9. So we're going to be looking in this row here. We're looking for negative 2.589, but obviously it's all positive, so we're going to look for where positive 2.589 would fall. And we see it falls between these two numbers right here. And if we, no, I'm sorry. It's going to fall between, there we go, between these two numbers right here. So we see that if we look up at the top here, it's going to be between 0.01 and 0.02. So if we go back, we're going to see from table B, our p-value will be between 0.01 and 0.02. Now, that's kind of a pain to actually have to do that every time, and it only gives you a range. So to use your calculator, you're going to use the TCDF function. So second vars will get you there. And you're going to do the lower boundary, the upper boundary, and degrees of freedom. So my lower boundary would be negative 100. My upper boundary was negative 2.589 and 9. And then we end up with a value of 0.015. And we see that this p-value did fall between what was stated from table B. So since our p-value is less than our significance level, we're going to reject the null hypothesis and have convincing evidence that the true mean hours of sleep for HF2 AP students is less than 8 hours. Now, because one of our conditions was not met, we have to make this statement. We must be cautious of our results as the independence condition was not satisfied. So if a condition is not satisfied, you can continue with the test, but then you must make the statement about being cautious about the results. Okay, so you can take a minute, pause, and just copy these down, but these are the important ideas. Again, checking your conditions, the random, the independence, and for normal condition for a means, if they tell you the population is normal, then you can continue on that your sample distribution should be normal. N greater than or equal to 30, we use the CLT theorem, the central limit theorem. If your sample size is greater than or equal to 30, we can state it's normal. But if neither of these are met, we will plot our sample data. You must show whether it's a dot plot, a box and whisker plot, a probability plot, histogram. You actually have to graph your evidence, and then if there are no strong skew or outliers, you can state that it is approximately normal. Again, if the condition is not met, you can continue the test, but after you conclude, you have to have this statement right here that we must be cautious of our results as whatever condition was not met. The test statistic, because it's for the mean, it's a t-test. The test statistic is a t-value, so it's the one sample t-test. This is the formula, and you must always draw your curve and state your degrees of freedom. We saw the p-value. We can use the table with the table B with the degrees of freedom and the tail probability to find a range for a p-value, but it is much easier to use the calculator and to do the TCDF, lower upper degrees of freedom. If you have a two-sided significance test, your p-value, you're just going to take your TCDF, whatever you calculate for that, and you're going to multiply it by 2. Okay, so you can pause the video and then you can try the check understanding and come back and see how you did. Okay, so in this check understanding, the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO's level at 30 randomly chosen locations along the stream. Here are the results in milligrams per liter. The mean is 4.77 and the standard deviation of the sample is 0.939. An average dissolved oxygen level below 5 milligrams per liter puts the aquatic life at risk. Does the data provide convincing evidence at the significance level of 5% that aquatic life in the stream is at risk? So again, in the 4-step process, it is expected that you have each of these listed. The parameter, we're looking for the true mean DO level. Our hypothesis is, our null hypothesis is that the true mean is equal to 5, but alternatively, we suspect that it could possibly be less than 5, which would put our aquatic life at danger. Our statistic, our sample mean was 4.77, and we are going to do a significance level of 5%. Our plan, the name of our procedure, since it's a mean, is a one sample t-test for the mean, and we check the conditions. And you're going to go through and check, and you're going to see the random checks, the 10% checks, and it's normal by the central limit theorem because 30 is greater than or equal to 30. The do part, state your general formula. T is equal to the statistic minus the null parameter over the standard deviation. For our T, it's going to be the sample mean minus the mean from the null over our standard deviation formula. Then you show your work and you plug it in, and you're going to end up with negative 1.34. You must draw your picture, you must label it T, you must have your degrees of freedom on there, and you shade in everything to the left since our alternative hypothesis was less than. Our test statistic then, we said was negative 1.34. You can use the table and it's going to come out to 0.05, between 0.05 and 0.10, but if we use the calculator, we're going to come out to 0.095, and we're going to see that that falls between what we would have found from the table. So if you were to interpret what your p-value means, assuming that your null hypothesis is true, so assuming the mean DO level is 5 milligrams per liter, there is a 0.095 probability of getting a sample mean of 4.77 milligrams per liter or less purely by chance. So what can we conclude? Well, our p-value is greater than our alpha, so we fail to reject the null and do not have convincing evidence that the true mean DO level is less than 5 milligrams per liter. Now, based on our conclusion, what type of error could we have? Type 1 or type 2? Well, what was our conclusion? Our conclusion is that we failed to reject the null hypothesis. So which error do we fail to reject the null hypothesis? That is a type 2 error, is where we fail to reject the null hypothesis. So that's the type of error we could make. A type 2 error because we failed to reject the null hypothesis. So if we fail to reject the null hypothesis, what is a consequence of this error? So we're going to describe the error in context and then give a consequence of it. Well, if we fail to reject the null hypothesis, the error we could make is stating that the alternative hypothesis is true. So we would say that we would determine that the average DO is actually less than 5 milligrams per liter when it wasn't. Okay, so that's the error we could make. What would be the consequence of that? Well, saying that it's less than 5 milligrams isn't the worst thing in the world because the aquatic life wouldn't die. Saying it's less than when it really wasn't, it would just cause the city or whoever is running this to maybe spend more money or have a lot of unnecessary worry or spend a lot of unnecessary time trying to fix the DO levels. Okay. All right, so for the last check understanding, it's a two-sided significance test because we have this game, Don't Break the Ice. You have the small plastic ice cubes, and the cubes are squeezed into a square frame. Each child takes a turn tapping out the cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. So the machine produces the plastic ice cubes designed to make the cubes that are 29.5 milliliters wide. But the actual width varies a little. To make sure the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The output summarizes the data from a sample taken during 1 hour, so we can see the output in our chart. Do these data give convincing evidence that the mean width cubes produced this hour is not 29.5? So since we're looking for that it's not 29.5, we're going to have a two-sided significance test. So we do our state. Do you remember what you need to state? Your parameter. It's the true mean width of the ice cubes. And I should have even added made in that hour. The null hypothesis is that the mean is 29.5. The alternative is that the mean is not 29.5. It didn't tell us what significance level to use, so we will use 0.05. And the means, the statistic mean from the sample, if we look up at our chart, is 29.4874. So then your plan, what type of test? A one sample t-test for the mean. You check your random, it checks. Your independent is going to check, and it's normal by the CLT. Okay, so the do, you need to give the general formula. You need to give the exact formula and then plug it in. Now here's where you want to be careful. You can use the standard deviation of the sample and divide it by the square root of n, which you see that up here, the standard deviation of the sample and divided by the square root of 50. But this is also known as our standard error of the mean. And our standard error of the mean is actually right here. We can see where that's calculated. So I went ahead and just used the 0.0132. But you can do it the other way and divide them out. You'll get the same answer. We divide this out, we get 0.9545. So we draw our curve. We should put a t there. I'm missing it, but you put your little t. State your degrees of freedom. It's 49. And you do 0.9545 and shade everything to the right, and negative 0.9545 and shade everything to the left. Now to find our p-value, we're going to do 2 times t CDF. Now remember, we had to do lower boundary, so we're not going to use this side. We're going to do negative 100 all the way up to our upper boundary of negative 0.9545 with the degrees of freedom of 49, and we get 0.345. Since our p-value is greater than 0.05, we fail to reject the null hypothesis. There is not convincing evidence that the true width of ice cubes produced this hour is different from 29.5. Okay, so continue to practice your 4-step problems. You must be detailed and do all the steps exactly as I have listed here. All right, have a great night.